For most of history, getting a diamond meant waiting millions of years for the crushing weight of the Earth's mantle to do the work. Early lab attempts mirrored this geological brute force, slamming carbon cores with millions of pounds of hydraulic pressure. We operated under the assumption that the only way to create this crystal was by fighting nature with extreme physical force. But today, materials scientists have found a way to bypass the Earth's engine entirely, growing diamonds inside low-pressure laboratory vacuum chambers. This phase diagram shows the traditional route. To stabilize the carbon, you have to push the environment deep into this high-pressure synthesis zone. However, at the very bottom left of the chart is the metastable zone, where diamond can form at near-zero pressure. This is chemical vapor deposition, or CVD. Inside a stainless steel reactor, a sphere of green or blue plasma glows in a vacuum. CVD directs chemical reactions to build the diamond lattice atom by atom, removing the need for geological scale pressure. The process begins inside a vacuum chamber, where a small, flat diamond seed is placed on a heated substrate holder to act as a template. Engineers then introduce a gas mixture into the chamber, primarily hydrogen with a tiny fraction of methane as the carbon source. Once the atmosphere is set, a generator blasts high-power microwaves into the gas. The microwave energy excites the gas molecules, stripping away electrons and creating a brilliant, glowing sphere of localized plasma. The kinetic energy within this plasma breaks the methane molecules apart, freeing reactive carbon atoms to drift toward the seed. This glowing microwave plasma replaces the crushing weight of the Earth's crust as the engine of creation. As those carbon atoms rain down, they face a structural choice. They can form ultra-hard diamond, or they can form soft, flaky graphite. Atomic hydrogen manages growth. It acts as a selective agent, removing graphitic carbon bonds while leaving the diamond lattice undisturbed, allowing methyl radicals to attach. Finally, hydrogen caps the surface, locking the carbon into a rigid sp3 structure and preventing graphite formation. Hydrogen effectively carves away structural errors in real time, ensuring that only the diamond structure survives and grows. Under this continuous plasma shower, the diamond grows layer by layer, atom by atom, over the course of hours or days. This scanning electron micrograph shows the result. Panel A shows individual pyramidal crystal structures forming a uniform base layer. By adjusting plasma gas ratios, researchers dictate grain size and thickness, seen in the variations of panels B and C. Because CVD builds the crystal with atomic precision, it transforms diamond from a scarce gemstone into a highly engineered, mass-producible material. These flat, lab-grown plates are not meant for jewelry. They're being engineered to solve massive hardware bottlenecks. AI computing is currently hitting a thermal wall. Chips are becoming so dense that traditional copper heat sinks can no longer move heat away fast enough to prevent them from melting. Because diamond is one of the most effective thermal conductors in existence, these synthetic layers are being integrated directly into microprocessors to pull heat away from the silicon. Diamond's high radiation hardness also makes it a candidate for space electronics and sensors operating in high-energy environments. Its wide bandgap properties also makes it useful for handling high-voltage loads in modern power grids. Diamond is not a replacement for silicon, but a complementary material designed to handle the thermal and environmental extremes of modern technology. This process turns invisible carbon atoms in methane gas into a perfectly transparent, geometrically precise wafer of diamond. This transformation relies on precise control over gas phase chemical kinetics and high-temperature plasma physics. The frontier of high-tech computing and space exploration now depends on the exact same crystal structure that people wear on their fingers. Share this with someone who loves fun facts.
Share this with someone who loves fun facts.